Okay, I printed off a lot of really nice notes for our speaker. Have you tried to see if your projection works? Need the sharing screen. Okay, that looks good. You can just leave it up. I'll just, since we're late because of technical difficulties, I'll just get going. I guess locally I'm going to stay co-host or something. So welcome everybody to the, I think it's the second to last CIIR talk of the spring semester. So we have Jiqun Liu, who's going to be speaking with us today. He is in the, well, he's got it on here. He's an assistant professor in data science and also an affiliated assistant professor in psychology at the University of Oklahoma in the School of Library and Information Science, I think, or studies, I think is what it is. He got his PhD from Rutgers in 2020, so just in time to start a career as in the middle of COVID. He is very interested in the intersection of information retrieval, human cognition, and human behavior. He studies things like debiasing results, recommendation results, and my favorite, which I've now forgotten, there was one that was really interesting in the list of stuff he looks at. So maybe he'll talk about it today. Today he's going to talk, as his title says, about understanding and supporting boundedly rational users in intelligent information retrieval. Here at the CIIR, we totally grok intelligent information retrieval. That makes total sense. I'm looking forward to learning what in the world a rational human is, rational user is. So without further ado, please join me in welcoming Jiqun Liu.
Thank you very much, James. Thank you for having me today. The title for my presentation today is Understanding and Supporting Boundedly Rational Users in Intelligent Information Retrieval. So I will introduce some of the recent works we have done on user modeling and bias-aware evaluation in the context of IR. So as we know, search has been a major core component of many different platforms, not just the search engine, and also it has been applied in places like digital library search systems and also on social media platform, which allows people to seek for information of different types across different platforms. So behind this system, there are a lot of things our community are trying to do. Not only understanding query or question or prompt, but also trying to find the right information, not just documents, but varieties of types of information to support information seeking, to meet, to satisfy information needs. So we need to achieve this, we need to not only look at queries, but also the user features and task features behind it, which requires us to do task modeling, user modeling, and combine the insights from HCI and IR. So that way we can look at not only the relevance between the questions and the documents, but also to what extent the documents or information are useful for the user to accomplish a certain kind of task, and to what extent users are satisfied with the information retrieved or provided by the system.
Did you
So,
get your eyebrow? Yes, I did.
So for to go beyond just finding the right documents for a given query, we need to consider how to provide intelligent support for a user in the task and also at the right time. So to achieve this, we need to first acknowledge that information retrieval is essentially interactive and dynamic, and people engaging in information seeking and search sessions that involve multiple search iterations. And people are not perfectly rational agents or optimized decision makers. So they are often affected not only by algorithmic biases, the biases related to certain sensitive labels, but also they are affected by their cognitive and perceptual bias, the bias that may be topic independent. So to achieve this, we need to incorporate the knowledge about user biases and task states into information retrieval evaluation, which allows us to not only understand the task behind the queries or question better, but also understand the users better, understand users as boundedly rational individuals. So that leads to the outline of our today's talk. I will first talk about our work on user systematic biases, talking about prediction and how to incorporate that into evaluation, and also task state modeling. How do we model the dynamic process of task completion in the context of IR, and how to develop adaptive or even proactive recommendations around that. And then we will talk about the vision we're trying to pursue with these different lines of research. So we'll first talk about user systematic biases. So as we know, there are many formal models that are built in not only in the context of IR, but also in the human information interaction in general. And in those formal models, we either explicitly or implicitly assume that users are rational in some sense. They are unmoved by emotions and external factors. They are always seeking maximize utility, and they have unlimited cognitive resources to do very complex computing to decide which is the optimal action, optimal step to take in this process. So that these kind of assumptions are actually problematic, which sometimes leads to the deviation of the prediction results from the actual behaviors. And that's because users are often affected by systematic cognitive biases. They're not always rational. They are not always looking for optimized outcomes. In many cases, they are not even aware of the optimal outcome, and they have a limited capability of information processing or to compare. They can't constantly compare different available options if they are aware of all the options at all. And in many cases, they often just go with the good enough or satisfactory option. So if we look at the structure of bias, we have many ongoing studies in both within and beyond IR, looking at data algorithmic biases. And in this study, we are trying to look at the other side of bias related to human. What are their human cognitive and perceptual biases, and how they affects the way people interact with information systems. So systematic biases actually refers to the systematic patterns of deviation from norm or rationality in judgment. And they are kind of ubiquitous in that they exist in a variety of tasks and situations and human system interaction activities. And since there are many different types of human information interaction and different kind of cognitive bias, in this talk, we are going to focus on one bias, what we call reference dependence. And also in terms of the application context, we're looking at information retrieval. So what is reference dependence? So according to the idea about reference-based evaluation, the carriers of value behind actions are gains and losses defined relative to a reference point, not the absolute value of final outcome. So here I'm going to explain this idea with an example. So imagine there are two people trying to move from one apartment to another. In situation A, the person is moving from apartment A to B, and the walking distance decreased from 25 to 10 miles. And in situation B, the other person is moving from apartment C to D. The walking distance increased actually from 2 miles to 5 miles. So in this very simplified example, if you only look at the final outcome, not looking at the implicit references, if you only look at the final outcome, it's kind of difficult to understand why the person A is happier than person B about this move because the walk home distance is actually larger for the first person compared to this person, right? But if you take into account the reference point here, 25 miles and 2 miles, then it makes total sense, right? Because when we make the judgments, we are not looking at the final outcome. We are actually looking at the relative gain and relative losses. So this is actually, this model is closer, have been empirically confirmed in many behavior experiments that this model is closer to to the way in which people actually make judgments and decisions, especially related to numbers and quantitative evaluations. And also build upon that, there's another effect called loss aversion, which refers to the phenomenon that assuming the amount of gain and amount of loss can be quantitatively compared, right? So assuming there is certain amount of gain and the same amount of loss, in terms of quantity, then the amount of pleasure comes from the certain amount of gain is significantly smaller than the amount of pain that the person feel from from the same amount of loss. So in other words, the pain you perceive from losing $5 is much bigger than the pleasure you get from getting $5, right? So if you put that in this in this figure, then the way it reflects is that the slopes here is deeper than here. You have large, so on the loss side, the user happiness or the pain, the happiness actually drops very quickly. But if you look at the gain side, for the same amount of variations, the pain, the happiness actually increase very slowly. So it's not, so they are kind of asymmetric. So this is what loss aversion actually refers to. So we introduced these two sort of the idea about these two effects into IIR user modeling and evaluation. So we include reference points to our models, not just look at the final outcome, but also what's the delta, the relative gain or loss compared to the reference point, and how they are related to search, how they affect search behavior, and how they affect user search experience, especially satisfaction. So to do that, we did a sort of experiments using user study data. We're trying to answer 3 questions. The first one is about to what extent are users' search behaviors and level of satisfaction associated with relative gain and loss? And the second question is about how the query level satisfaction associated with session level search satisfaction. So many of the IIR experiments are conducted at query level in ad hoc retrieval context, and how we put this idea in session, whole session evaluation, then how query level satisfaction or query level experience related to session level experience. So this is what we're trying to figure out with our RQ2. And for RQ3, we put that into application and trying to figure out to what extent we can improve the performance of prediction with reference-dependent metrics. So this work's actually published in CIIR 2022. So to facilitate this experiments, we employed user study whole session search data from 3 different data sets, which gives us over 1,800 whole search sessions and over 5,000 query segments for the experiments. And to build the reference dependence values, we actually simulated a set of reference points based on the findings from previous behavior economics literature. So the first reference is the peak value. For example, what's the most satisfactory, what's the highest satisfaction score in the past interactions? What's the the largest number of pages visited or clicks made in previous interactions up to this point? And what's the end value, which is the most recent query segment, and average value up to this point? And reference level 4 is a combination of 1 and 2. So with these set of simulated reference points, simulated based on previous literature, we built a reference-dependent model, simply looking at the delta, the difference between the measure, the final value, and the reference value, right? And we did this for each online and offline measure. So basically, for each measure, we have 4 different reference-dependent metrics. So we have included a list of online and offline measures from different places, which captures mouse movement behavior, clicking behavior, and also the offline evaluation metrics. And for each measure, we calculate their reference-dependent metrics based on 4 different reference levels. So in terms of loss aversion, we found that on the negative side, where the measure, the score is the score is negative, or meaning the measure is is not as good, the measure is not as good as the reference point, then is significantly correlated with user satisfaction. On the positive side, it's not so much significant correlations. So which means that users are more sensitive to the perceived losses in terms of behavior, in terms of information gains, with respect to query level satisfaction evaluation, right? So if you look at this figure, you look at the negative side, you will see more significant correlations compared to the positive side. So for RQ2, we look at query level satisfaction and session level satisfaction, trying to connect users' local experience to their whole session experience. Right. So before we introduce this study, I would like to introduce a little bit about the motivation or the idea that inspires this research here. So previously, in one of the behavior economics research, there are a bunch of researchers who have done pain intensity study for colonoscopy process, right? So they have 2 patients, patient A and patient B. They both go through the whole colonoscopy process, and there's a researcher asking them to report their perceived pain intensity for either every 30 seconds or every minute, right? And then they take the value and have this 2 figures, right? So if you look at the figure, you will see that for patient A, the whole colonoscopy process is like 8 minutes, and for patient B is like almost 25 minutes, right? And if you look at the shaded area, it's clear that the total amount of pain that patient B perceived is significantly higher than that of patient A, right? So now the question the researcher asks is that who gives a lower rating for the entire colonoscopy experience? So they found that actually patient A gave a worse retrospective evaluation, despite the fact that the shaded area is significantly larger for patient B compared to patient A. So they found that this is because the way people evaluate a session is very different from what we normally assume, right? So they are what they call peak and roll, where they found that the impacts of peak point and end point are very significant, right? So if you look at comparing these two, you find that the end point for patient B, the pain intensity is very low, lower than 2. And for patient A, the end point is almost like over 8, and even for the last minute, it's over 6, right? So this like partially explains why patient B gives a higher evaluation score compared to patient A. And they found that the correlation between the duration and the session evaluation was low. So the length of the session does not matter so much, right? So the final conclusion is that remembered utility is more important than experienced utility. So when we ask a user to evaluate their experience with a new system or new interface, new tool, they actually rely on not their experienced utility, because experienced utility kind of evaporated once you finish that moment, right? So they are actually making their judgment or decisions based on the remembered utility. So for the remembered utility, they found that duration, a total amount of of the cost efforts does not matter so much, and they found that the peak and endpoints actually are significant in affecting the whole session evaluation. So we borrow this idea to the whole session evaluation in the context of IR, and we found a similar thing where we have compared the peak end model with this simplified baseline model where we only employ the traditional average-based and some value-based measures. We found that in the peak end model, we have higher R-square value, and we found that both peak and endpoints have a significant impact on whole session evaluation. And we also find that the session dwell time doesn't matter so much, same thing for the total click count and total query numbers doesn't matter so much for whole session evaluation. So it's important to note that things like dwell time, whole session dwell time, and total clicks and query numbers and documents visited, all of these measures are widely used in many of the models we built to model users' search costs. Right? So when we model search costs, we often use those values to as a sort of representation of the search costs and connects that to user experience. But with this study, we found that it doesn't really, people don't make judgments that way. We should probably pay more attention to the peak endpoints. Right? So this is consistent not only in this study, but also in many different areas where people have done behavior experiments. So for example, when people evaluate a TV series, they found that the best episode and the last episode, the end of the story, actually have a major impact compared to every other episode. So probably the first episode also matters to keep people just stay on the TV series. But it's not like we can use the average score across all episodes to accurately represent the whole TV series rating or evaluation. So RQ3, we come to the application point where we incorporate the reference-dependent measures into prediction, and we found that they actually gives us better performance compared to even to the best performer, which use the traditional final value-based measures. And takeaways from this research, we found that users' level of search satisfaction are significantly correlated with gains and losses, not just the final outcome. And users are more sensitive to losses perceived in the process. Right? And also session level satisfaction is significantly affected by peak and end moments. And models employing gain and loss-based reference-dependent features achieve significantly better performance in prediction. And then we take a step forward by developing reference-aware information retrieval evaluation. We simulated relevance-based reference points based on the relevance score assigned to individual documents. And we adopted the CWLA offline evaluation framework, and we're trying to incorporate the simulated reference points into the different components of the CWLA framework. And then we meta-evaluate our evaluation measure against the traditional widely used offline evaluation measures in terms of correlation with query level user satisfaction. So we have changed multiple parts of CWLA framework. So here I'm just showing you an example about how we change it. So this is the probability of continuing browsing at rank I, and we incorporate the reference points to to the denominator, and we used different types of reference point extracted from previous literature. And when we do the evaluation, we found that our reference-based measures actually outperform many of the traditional offline evaluation measures with fine-tuned parameters. Right? And then in one of the data sets, we found that our measure have a similar performance with the expected reciprocal rank. And in other two of the data sets, we outperform all the other measures. And then we again evaluate our measure in terms of the discriminative power, in terms of the ability of those measures to differentiate good performing systems from other systems. And we found that our measure have close or sometimes better performance compared to most of the measures, and significantly better than expected reciprocal rank. So the ER has a similar performance with our measure in one of the data sets, but then we run this discriminative power analysis. We found that our measure is significantly better than the expected reciprocal rank. So if you combine these two parts together, you will find that our measure actually in total outperforms all the offline evaluation measures we included here with the fine-tuned parameters. And then we kind of conducted another user study where we tried to find the empirical evidence about reference point. Right. So in previous studies, we employed different user studies data sets, some of the data sets from our previous studies, some of the data sets from other labs. But when we trying to do the evaluation or trying to do the model building, we had to simulate different reference points, right? Because we didn't have the direct evidence there. But here we conducted another study where we're trying to figure out what are what information that or what signals that users actually employ as their reference points. And we find out from our user experience, we found out that users often use their local expectations as sort of reference in their judgment, in their evaluation. So in this user study, we actually collected information about user expectation at a query level, where when user, so in the study, when user issue a query before we retrieve the CIIR, the system actually gives a pop-up window to the user where the user can annotate their expectation about like how many useful pages they expect to collect under this query, and how many clicks they kind of expect to make, and how much time they kind of expect to spend under this query segment. And then we did that we did a correlation prediction with those this reference point annotated directly by users. And we found that there are significant correlations between those behavior measures and their different parts of their expectations. And also we look at gain confirmation, effort confirmation. So when gain confirmation is positive, meaning the amount of number of useful pages they end up collecting is exceed the number of useful pages they expect to collect, then it's significantly associated with a higher satisfaction level. And on the other side, if the efforts they spend is higher than the effort they expect to spend, then it's correlated with a significant lower satisfaction level. So we also conducted prediction experience, evaluation experience with this reference point in a similar way we did with other user study data, and we found similar results. With those reference points, we have better prediction and evaluation performance. So that's for the first part about this talk. And the second part, we move from user to task. And specifically, we're trying to figure out how to model tasks dynamically and how to to build adaptive recommendations based on that. So to do that, we need to introduce an important concept called task states. So in many of the previous studies in task modeling, we have modeled different static parts of static dimensions of tasks, especially the dimensions we can sort of pre-annotate or predefine before the user actually start doing the task, right? So for example, like task complexity, task type, task difficulty, task structure, topic familiarity, and domain knowledge. So many of these labels we can ask users or domain experts to annotate before the user actually start doing the task. So what we're trying to do here is that we're trying to argue that the knowledge about task states or the dynamic process through which user complete the task is also important for task modeling and for supporting users. So so that's why we did state-aware task modeling here. And we first, after collecting the data from user studies, we asked two IIR PhD students did back-to-back annotations of query level task states based on this typology, exploration, exploitation, no item, and learning evaluation, which corresponds to different kind of intentions at local level. And we did this, back-to-back annotation and discussion, several rounds of discussion until we have this acceptable agreement among these annotators. So with the data, the question we're trying to answer is that, can we differentiate tasks of varying types based on their state transition patterns? So the short answer is, to some extent we can. So we modeled the state transition patterns under different types of tasks. We found that different task types are associated with different state transition patterns, and we can actually predict task state from search behaviors, which sort of set the basis for us to provide adaptive support for users in longer search sessions. So with knowledge about task type, task state, we're trying to do adaptive recommendation for users. So for example, here we have one user who have their original search session. So each arrow actually represents a query. So this search path shows how user navigate this problem space and gets to the point where she either complete the task or completely give up. Right? And we have this information about the states and information about the query. And what we're trying to do here is that we're trying to, for similar kind of tasks, we're trying to automatically extract query segments from other users. I'm trying to combine that and reduce the number of steps the user needs to complete the task requirements. Okay. So to achieve this, we employed a reinforcement learning-based approach, where we have the algorithm first trying to figure out what the state the target user is at based on the search behavior. And for the action, based on state, the algorithm needs to decide the action. The action refers to ranking. Here is ranking, different ways of ranking available query segments and taking the top one as the recommendation. So different action refers to different ways in which we rank those query segments. And then we will take these query segments back to the user's search path, assuming that the user, since this is a simulation-based experience, we assume that the user take this recommendation as his or her next step. And then we can get the reward based on whether the recommended query segments actually helps the user move forward towards completing the task. So in this study, we have a very clearly defined task, and also we have clear, requirements and, for example, number of useful documents or the steps the user need to take to achieve the task completion point. So it's pretty well defined and an environment for reinforcement learning training. So after several number of rounds of iterations, we found that our recommendation approach can help users complete the task sooner. So it only, not only surpassed the original search session, after some rounds of iteration, and also it gets to the actual completion point very quickly. The difference between these two is that in some of the tasks, user already, complete the task requirements, but they are not aware of that simply because they are not familiar with the topic, and they keep on searching for information, keep on issuing several other rounds of queries, and when we apply this recommendation algorithm, we found that our algorithm can get to the theoretical optimal point where we can stop at the actual completion point rather than the original, not only just surpass the original completion point. So that's about task state modeling. And then we'll talk about our vision with these lines of research. So in our study, we have explored different types of features or signals, including both observable features and also implicit factors. So here I highlighted the factors that we included in this talk, in the research I introduced today. And there are also other types of signals or cues or factors we can include for modeling users, predicting users' biases, and develop bias-aware bias mitigation approaches. So what we're trying to do here is that we're trying to figure out what's going on under the water. There's a major part under the water going on in terms of with respect to human information interaction based on what we can observe here. And then with the knowledge we learn about the implicit factors, then we can support what's going on about the water, like the observable interactions, conversations, and also information judgments and evaluation. So this is kind of the roadmap we developed based on our lines, kind of guide our study. So we're trying to address both algorithmic and human biases. We need to not only look at the labels we use when we try to identify and address algorithmic biases, but also the models we need to address to understand human bounded rationality, to address the negative impacts of cognitive biases, like the prediction models we built to predict human biases, and also the re-ranking recommendation models we employ to de-bias and also mitigate bias on both human and algorithmic side with the intelligent nudging techniques. And also we need to have bias-aware evaluation models where we capture both the search effectiveness measures and also the bias reduction measures. So here's a list of recent research we have done. Some of these are cited in previous slides, and also we have a recent book published in March 2023, where we include both the biases and experiments we introduced in this talk, but also some other biases that are empirically examined in behavior studies, but not studied yet in the context of information retrieval, conversational search, or recommender systems. So there are still a lot of future challenges we need to address with these lines of research, like this tornado ahead of us. We need to, in terms of research, they are sensitive and expensive and time-consuming process of labeling, right? So, for example, in one of the studies, we collect labels about user expectation. We certainly need other labels that are related to cognitive biases. They may be difficult to collect. In some of the contexts, users are not aware of their own biases, so that creates methodological difficulties for studying this. And also the privacy protection in user modeling. So what kind of information we need to build a bias-aware user model, and how do we protect user privacy in application, right? So for example, we help user develop really informative prompt to ChatGPT, then how do we ensure users' privacy is properly protected in this interaction process? Why are we getting useful information to the user? And also evaluation, we need to consider many different dimensions, and what level of control do we give users? Do we just directly do direct intervention, do re-ranking of the results and recommendations without letting users know, or do we just simply send reminders or of possible risks of biased judgments, but not like intervene any of the judgments or behavior process at all? And also there are diverse modalities of interactions we need to consider. And beyond giving the right answer and documents, how do we help users ask useful questions? So this may be more important for the context of chat search. So to answer those questions, my students and I are conducting many different types of study to collect the labels evidence we need, including lab studies and also remote naturalistic experiments and cross-section study on user biases, algorithmic fairness, and misinformation. So these studies are largely supported by the National Science Foundation grant we get for doing bias-aware user modeling in IR. All right, thank you for your attention. I'm happy to take any questions you have.
So much. A few people here. Does anyone have a question right off? Oh, they're laughing and smiling. So either they're watching TikTok videos or they love the talk. I'm not sure. I have a question. You showed that if you gave the user a particular expectation, so to just set their reference, like this is the normal number of clicks, or you ask them to give it, then that would affect whether they felt happy or sad about what happened. And it made me think of the colonoscopy example, where if you had told the person who had the very short but painful colonoscopy that all colonoscopies take a minimum of 30 minutes, that maybe they would then be really happy. So it made me wonder, does this mean we should just lie to people to set their expectations really low so they're always going to be happy? Would that work in search engines?
Yeah, that's a great question. In this user study we have done, we actually asked users to report their own expectations rather than plugging any predefined expectations. I think many of the in e-commerce context, the people are constantly doing that, right? So, for example, if I tell you a pair of shoes is $50, it's kind of difficult to predict whether you're going to buy it. But if I tell you that it was $200 before, then you're probably going to buy it because that gives you a sense of gain in this process. But in the context of IR, especially in terms of study, I'm not sure if giving them, just telling them, certain average number across the board or average number at a population level, I'm not sure if that's going to be an effective way of building in references. Right? So in our user study, we are trying to infer what's the right signal about a user reference. How do we infer user reference from their behaviors from that, rather than trying to test the reference-aware, reference-dependent effect, because we already have evidence on that. And actually, in some of the studies, we did try to build in to assign predefined reference point and see how that affects behavior. But we haven't. We're still collecting data. We haven't got to the point where we have conclusive results from that.
Cool.
I have a question. I actually asked in the chat, but I'll read it loud. So thanks for the talk. In recent years, the last couple of years, we see a lot of excitement around user simulation, especially using large language models. And in these simulations, it's often feasible to kind of control user behavior. So for example, patient users, inpatient user, and things like that. So I'm wondering, what do you think about these approaches for IR evaluation? And for example, using all the dimensions that you talk about, what do you think of, for example, using these dimensions to control user simulations in these environments?
Yeah, that's a good question. I think it's feasible, apart from the problem question about whether we should do it or not. If we're only looking at the feasibility, I think that's kind of feasible. If we have the, assuming we have the knowledge about their, about their biases, and especially the major biases that affects their behavior and judgments a lot, we can incorporate that into the user simulation, into the user models we built, because many of the studies, including the studies from HCI or from cognitive psychology, we found that the knowledge about user biases, we include that into system building or interface that helps us to build this sort of cognitive alignment between the system and the user. So that way, users are more inclined to be engaged with the system or trust what the system presents. So that way, kind of increase the feasibility of controlling user in this interaction process. But there, of course, there are ethical issues and privacy issues comes with that. So just like the example we gave in the context of e-commerce, very simple example. It's $50 shoes, but if I tell you it's $200 before, and this is like a Black Friday deal, then it sort of significantly increases the chance of this pair of shoes being bought by some users, right? So that's to some level shows the way in which we can influence, at least influence or even control user behaviors. So I think if we include that into evaluating IR systems, the major challenge we need to consider is that what we can use as the right ground truths, right, for evaluating the system or meta evaluating evaluation metrics, because some of the interaction patterns like chat search or chat or other forms of large language model applications, it may help increase the level of satisfaction or level of engagement a lot, right? So assuming we are using this as sort of ground truths for evaluating metrics, evaluating systems, then it gives us good performance. But it may gives the good performance in improving satisfaction without actually improve the effectiveness in doing the IR job, the real IR job, like finding useful, credible information. It may be able to make user happy without doing that. So if we think about this problem from the evaluation side, we need to really think about what kind of ground truth measure we can actually rely on for future evaluations.
Thank you.
Okay, so I have another question since people are being silent. So in that work you talked about with Chirag, where you were sort of recommending quicker paths to accomplish the search. I didn't really understand what that would look like from the user's perspective. I sort of got the idea that you've learned with that reinforcement learning system, you figured out that there's a faster path to get to the end result. But what does that look like to the user? Is it the case that that the user is given sort of query suggestions or task shortcut suggestions or something like that? What does that look like? What would it look like if it were actually implemented and run? Yes,
it's sort of path recommendation where we recommend a query plus the SERP to the user, and then we consider the utility or number of useful documents we can get from this combination as the reward, and feed that back to the reinforcement learning algorithm to facilitate this whole simulation process. But for we actually implement this, then there are a lot of factors on the interaction, the interface part we need to consider, whether this is going to be like a tool on the sidebar or going to just directly swap the query recognition, the original SERP with the extracted SERP, or do we provide like 2 or 3 different paths for users to choose from? So there are a lot of open questions that we were not able to address with this simulation study.
Does that whole, so I remembered, because you actually mentioned it in one of your last slides, that the thing I liked in the work you described, the term I liked was intelligent nudging. Is that an example of intelligent nudging? Or would that be an example of intelligent nudging if it weren't just simulated?
I think it's more, this is more, I think intelligent nudging would be more sort of indirect or implicit compared to interventions like this, where we explicitly provide those. So here we explicitly provide the recommended SERP and doing the re-ranking, all that's more explicit or more salient. Right? So we intelligent nudging would be more, what we're trying to do right now is that we're trying to provide more sort of indirect, implicit, treatment for users. So they are, it provides, it can nudge users and push users to a more effective path, or to the kind of behavior we're trying to promote, without they are like without they being aware of this process. So it's going to be more implicit.
I see. Okay, well, that's very good. Thank you. Are there any other questions? I'm looking to see if any hands are raised. If there's no other questions, I think I'll have opportunity to talk to you later. So we can thank Jiqun one last time. Thank you so much for your wonderful talk.
Thank you.
And I think we will see you there's another Zoom link you have, and we'll see you there in about 3 minutes.
Thank you. See you there.
Okay. Thanks a lot. Bye-bye.
Yes.